Yeah, here is a simple example how to relating how to relate the coulombs to the quantity of reaction. Okay, the question is if 5.585 grams of ferric ion were reduced to ferrous ion. It is reduced because the oxidation state becomes smaller. Okay, how many coulombs of charge must have been transferred from vanadium 2 plus to ion 3 plus? Okay, and then what is the reaction here? This is reaction, yeah? We've just seen a few minutes ago here. Okay? And how do you know how first we have to know the how many electrons are transferred from vanadium, divalent vanadium to ferric ion. Okay, of course one electron. Okay, one electron is involved in this reaction. All right, and the this amount of ion actually how many moles? So we have to know the atomic weight of ion. Okay, atomic weight of ion is 55.85 gram. Okay, per mole. This is 1 mole. All right, but in the considering the um, moles, yeah, we simply ignore the weight of here 3 electrons. Actually, this is well, 3 electrons deficient of ion. Okay, but electron mass is so light. Okay, so we usually ignore when we consider the mass of this ion. Okay, you simply take the atomic mass here. So this amount of the ferric ion actually, if we divide by atomic weight of ion, then we can get 0.100 mole ferric ion. Okay, so this one ferric species receives 1 electron. So this amount of ferric species what receives this amount of electrons. Okay, so number of electron is 0.1 mole. Okay, so total charge is using this equation Q equals N times F. Okay, N is 0.1 mole electron here, right? And then F is constant. Yeah? This is Faraday constant, so you have to memorize this constant. Okay, so we get this number 9.649 times 10 to 3 coulombs. Okay, so in this direction. Alright, as I said, electric current, usually we can measure the current in electrochemistry. Current is flow of electrons. Okay? When electrons flow through the circuit, then we can, that is a current, but the direction is different. Okay? Direction of current is opposite to the electron flow. Okay? So 1 ampere is defined by 1 coulomb per second, or 2 coulombs per 2 seconds, or 0.5 coulombs per zero point 0.5 second. Okay. Okay. Let's consider more about electric current. Okay, as I said here, current, as I said, current is a measure of a reaction rate. Okay, so if you measure, let's assume you measure the current. Okay, that is the reaction rate. Okay, it itself. Here is a example. This standing ion. Okay, this is 4 plus, okay, state is reduced to stannous ion. Stannous ion is divalent one, right? The trivalent stannous, the tin ion is very unstable. Usually, this one tin uh, takes +2 or +4 state. Okay, so here 2 electrons are involved. Okay, this one receives 2 electrons to become this one stannous state at a constant rate of this one 4.24 millimole per hour. Okay, how much current passes through the solution? Yeah, this is the simplified structure. Okay, here electrons are provided from this side, but we don't we don't care. There's another part. It's simply we assume that electrons are provided from other source, and the electrons now is provided through this the conductor, this circuit, and here, and this one, this coil. I think this metal may be the platinum, and then it what inserted in this solution containing this one, stannic iron, right? And then electrons now uh, go to the stannic iron, and this iron becomes to xenos. Okay, and question is what? How much current passes? Okay, current. Let's now calculate the current. Okay, the first we have to write correct equations. Here, this one is equation. Okay, one thin iron reacts two electrons. Okay, so how many electrons are let's first calculate electron flow rate. Now constant rate of this one. Okay, so we know the reduction rate, yeah, which is this one. Okay, and what, since one stannic ion now reacts with two electrons, now electron this flow rate is what, two times of this one. Okay, 4.24 mole per hour times 2. Okay, this is electron flow rate, but now it is expressed by hour, but we have to convert into what, the second. Okay, and millimole now converts to what, mole. Okay, so first we divide by 1000 to convert this millimole to mole, and also we divide by 3600. Okay, because 1 hour corresponds to 3600 seconds. Okay, and then the electron flow rate is 2.356 times 10 to the minus 6 mole, okay, per second. Okay, this mole is electron mole, right? And now we are ready to calculate the current. Okay, by definition, current is what? Current is charge divided by time. All right, and here this mole now we multiply by what, Faraday constant, to convert this mole to charge. Okay, here, and then it is already divided by the second. Okay, and then we get this number, 0.227 coulomb per second. Yeah, coulomb per second is what, this is that is current ampere. Okay, very simple, very easy, but you have to understand. All right, but in electrochemistry, not only the current, but there are other quantities we have to concern about. Okay, the voltage, work, and free energy. What is the work? Now, work is the same as energy. Yeah? So unit is joule. Okay? Notice these relations are so important. You have to memorize these equations. All right. Work is this one, E is unit is volt. Yeah, this is potential. Okay, or voltage, same. Potential multiplied by charge. Okay, that gives the work. The unit is joule. All right, this one. Work done on surroundings. You know the from the second law of thermodynamics. Then you'll find that Gibbs free energy change, yeah, is related to electrochemical work here, right? It is given by this equation. Delta G, yeah, this is Gibbs free energy change equals minus NFE. The exact derivation is found in the physical chemistry textbook or electrochemistry textbook, more advanced textbook. But at this moment, you simply accept delta G Gibbs free energy change equals minus NFE. Okay, so whenever the electrochemical work is done, and then there is a Gibbs free energy change. Okay, why is it so important? Yeah, it implies many things, because you know, if delta G is greater than 0, that is what? That reaction does not occur spontaneously. Okay, when if delta G is smaller than 0, okay, and then that's a spontaneous reaction. Okay, but actually measuring Gibbs free energy change is very difficult, very cumbersome. Okay, but since this Gibbs free energy change is related to this electrical potential, by this one, and then if possible you can measure the electrochemical potential E here, right? And then we can immediately know the Gibbs free energy change here. Okay, what it is, there is a negative sign here. Okay, you see, N is the number of electrons. This is all the time positive, and Faraday constant is positive, and E could be a it has minus sign or mm, plus sign. All right, and then current is expressed by this equation. Yeah, we already seen that current I equals Q over what? Time. Okay, charge divided by time. But this one is also holds. This is called which law? This is Ohm's law. Yeah, very simple. Ohm's law. Current is potential divided by this R. R is resistance. Okay, and there is another quantity, electrochemical quantity, which is power. In Korean, power is what? 전력. Okay, 전력. P equals work. It is work per unit time. Okay, P equals work divided by this one, time, and here work is E times Q, and divided by this one, and then Q over S is what? This is current. Okay, so power is very simple. Power equals potential multiplied by current. Okay, so all these quantities are so important and so fundamental in electrochemistry, so you have to memorize it. Okay, and this one, let's look at these two figures. Yeah? And this is kind of analogous the picture to the electrochemistry. Yeah? So electric current is a analogous to volume of water per second. Okay, through this pipe, water now what flows, right? And then what is current? Yeah, current is the volume of water per second. Okay, that's the current. Yeah? That's the analogy. Okay? But what about the potential here? Potential is kind of pressure. Okay, electric pressure here. So if you lift this water reservoir high, and then here, hmm, this one, it what? Hmm, it exerts higher pressure, and then water flow, is that this becomes faster. Okay, so this one high pressure, that is correspond to voltage. Okay, but if you lower this water reservoir, and then the pressure becomes low also, so this water flow rate becomes slow. Okay, you understand? So when the uh, the resistance is the same, the higher voltage means here is like a higher pressure, so current becomes higher. Yeah? So from this Ohm's law. Okay? This relations are so important, so fundamental in electrochemistry. Okay, so I really urge you to memorize all these relations. Okay, yeah, this is a really simple electric circuit. Okay, here is a battery, ordinary battery, or lithium battery, or what dry cell, or the lead acid battery, used in a car. Okay, and then okay, let's assume you have a 3 volt battery, right? This is E here. Okay, E. And then here is a resistor. Yeah? The unit is ohm. All right. The symbol is R here. And then what is the current? So this one, current now flows from this positive terminal, and then through the external circuit, and then it goes back to the battery. Okay, that's the definition of current. Current flow definition. It comes from this plus terminal. But what is the electron direction? Is exactly opposite. Electrons are uh, come out from this negative terminal, okay, and then it moves through the circuit, and then it enters the positive terminal, okay, exactly the opposite. Okay, here is the electron flow in this direction, or current flow this direction, okay, yeah, here. And for current to flow the electric circuit, this should be a closed circuit, okay. And now let's assume you put a switch here. If you open the switch, since the circuit is broken here, and then there is no current, okay? Current only flows when the circuit is closed, okay? And what is the current here? From the Ohm's law, we divide this 3 by 100. So current is 0.03 ampere here, okay? Very simple, very simple. Okay, now let's consider electrochemical cells. There are two types of electrochemical cells. One type is galvanic cell. Galvanic cell means in galvanic cell spontaneous reaction takes place. Okay, spontaneously, the electrochemical reactions take place in galvanic cell when we make a closed circuit. Okay, open in an open circuit, although that cell spontaneous reaction could take place, but when the circuit is open, no current is there. Since this is a spontaneous reaction takes place, electrochemical cell potential is larger than zero. In other words, Gibbs free energy change is smaller than zero. Okay, as I said, this one. If this one positive, and delta G must be negative. Okay, this is the galvanic cell, and there is by the way, what are examples for galvanic cell? Can you name them? Your battery, yeah, battery is a galvanic cell, yeah, yeah, it generates electricity automatically, yeah, and what else? Yeah. Fuel cells are also galvanic cell. Okay, you will see soon. And by the way, electrolytic cell, non-spontaneous reaction takes place in this cell. No, the reactions are not spontaneous. Okay, in other words, cell potential is less than zero. As a result, delta G is greater than zero. Okay, that's the electrolytic cell. What are examples for the electrolytic cell? You see, the electrolysis cell, for example, water electrolysis. You know that when water is electrolyzed, and then oxygen and hydrogen gases are evolved, right, from water. But that reaction is not spontaneous. So you have to apply electrochemical energy. Okay, so that kind of cell is called electrolytic cell. All right, let's consider um, this type of reaction. Yeah, to make electrochemical cells, you have to have two electrodes. Yeah? One electrode is called anode, and one electrode is cathode. Usually in the figure, on the left hand side electrode is anode. Okay, you put cathode on the right hand side. Okay, and by the way, what is the anode and what is cathode? anode is the reaction where the oxidation takes place. In Korean, anode is 산화전극. Okay? 산화가 일어날 때 그 전극을 에노드라고 이렇게 부릅니다. And cathode is the electrode where the reduction reaction takes place. In Korean, 환원전극. Okay? So you have to have anode and cathode at the same time. If you remove one electrode here, yeah, nothing takes place. Okay? So to make complete electrochemical cells, you need two electrodes. Okay? And here, and then in the beaker, yeah, you put cadmium, metal and silver metals here in the beaker, and then in the beaker, inside beaker, cadmium chloride solution is there. Okay, and then let's consider what happens in the beaker. Okay, and this silver iron surface, you see, you you put this silver chloride, this white crystal, white solid, right? Usually, in the presence of this chlorine, iron, chloride ion, and then silver usually the reacts with chloride ion becomes silver chloride. Okay, this is quite a usual case. Silver metal, and in the on the surface, silver chloride is formed. Okay, and then this is cathode. Since this is cathode, and what reaction takes place on the cathode? Reduction. Okay, and this one, silver chloride, is reduced by accepting electrons. Okay, becomes silver metal, and two chloride ions are formed. Okay, this is the reaction that takes place in on this cathode here. Okay, but what about the on this anode? This cadmium, yeah, is oxidized. Okay, since this is the anode, so this cadmium metal becomes oxidized to cadmium ion, releasing the electrons here. Okay, and then the total reaction is that you combine this reduction and oxidation together. So if you add this reaction together, then you can write this one: cadmium, solid cadmium plus silver chloride. Two silver chloride is cadmium, divalent cadmium and silver metal and chloride ion. I'm sorry, the negative sign is missing here. Okay, yeah, this is a net reaction. But net reaction, electrons doesn't appear here. Okay, but actually electrons are what? Comes out of the this cadmium metal, and it enters this silver chloride. Okay, that's the we call this each reaction what the half reactions. Okay, and electrons actually net reaction, uh, electrons doesn't appear, but actually electrons come from the one electrode and enters other electrode. Okay, yeah. And someone measured the Gibbs free energy change in this direction, and then he got the delta G equals minus 150 kilojoule per mole of cadmium. Okay, now, what is the cell potential? What is the cell potential? Well, yeah, we can we can use this equation. Okay, delta G equals minus NFE. Okay, that's the a very important relation. So E cell equals minus delta G divided by NF. Okay, here the delta G is already known. Yeah? Minus 100 times 10 to 3 because this is kilojoule, and divide by the number of electrons. Yeah? Since this is per mole of cadmium, 1 mole of cadmium involves 2 moles of electrons. Okay, so you have to divide by 2 and also divide by Faraday constant, and then you can get 0.777 joule per coulomb. What's the unit of this one? Joule per coulomb. That's a volt. Okay, volt. Very simple, but very important. Okay. Okay, and then let's consider this type of cell, electrochemical cell. Here in this case, simply the silver ion here, right? Not silver chloride on the silver surface, yeah? And then solution contains cadmium ion, nitrate ion, silver ion, and nitrate ion. Okay, and this is cathode, and this is anode. Okay, and cathode reaction is the reduction. Silver ion now accept electrons to become silver metal, and in anode, cadmium metal, dissolves to cadmium ion, releasing electrons. What the total reaction is that cadmium metal plus silver ion is cadmium ion plus silver metal. Okay, yeah, this is the net reaction. But we can ask this question: can above reaction occur as we intend? But actually, this reaction doesn't take place. What would be the problem? What's the problem in this case? Our intention is to derive these cathodic and anodic reactions, okay, by setting up the electrochemical cell like this. But actually, nothing will happen. Why is that? Why? The, the answer is that all these species are in the same beaker, okay? Same beaker. And in this case, the reaction, this equilibrium takes place immediately, okay? Under the equilibrium condition, nothing will happen, okay? So, so you have to solve this one, okay? Which means that you have to drive the each reactions, okay, individually, separately, okay. That's the answer, okay. You'll see, soon. Okay, let's stop temporarily here. All right.